Hello everyone. I am Himanshu Mishra, and I am the PhD research scholar in the Department of Applied Mechanics. Today I am going to discuss question related to the radiation heat transfer. In the last week, I have discussed some question related to the basic heat transfer as well as recap few question related to the heat exchangers from the NTU principle. So this week we will be discussing some question related to the view factors and how the heat transfer due to radiation take place if we have arbitrary surface oriented in the arbitrary directions, and the radiation heat transfer will depend upon the orientation of the surface and the way it arrange in the system. So this will be given by the view factor, and for the different view factor the radiation heat transfer will change, and we will look some couple of problems related to that. So there will be some problems related to the heat transfer due to radiation, and there will be some problems where we have to find the view factors in the arbitrary geometry or the orientation of the surfaces. So let's start with the first question. So in the first question, there is a furnace cavity which is in the form of cylinder 75 mm diameter and 150 mm length, is open at one end to large surrounding that are at 27 degrees Celsius. The sides and bottom may be approximated as black bodies, are heated electrically, are well insulated, and are maintained at temperature of 1350 and 1650 degrees Celsius respectively. And we need to find the power required to maintain the furnace condition. So basically we are required to find the heat transfer, and we have given the temperature of the sides and the bottom wall, and the ambient temperature is also given, and we have given the geometry. So we need to find the radiation that is emerge from these sides and the bottom to the outside, because outside is a lower temperature, so there will be heat transfer due to radiation from inside the cylinder to the outside surroundings. And how much radiation will be emitted from the sides as well as from the bottom to outside, it depends upon the view factor. So we first need to calculate the view factor from the sides as well as from the bottom, and then we will be using those view factors to calculate the heat transfer. So in the question, it is given that all interior surfaces are black bodies. So let's define the surfaces first. This is my interior cylinder, and let's say there will be heat transfer from inside to outside Q. Let's say this is my area A1, surface 1 here. This is my surface 2 having area A2, and this is the outside region which I am marking as surface here as region 3. So now the heat transfer will be defined as, so there will be heat transfer from surface 1 to 3 because there is a radiation which is emitting from this surface to outside, and there is a heat transfer due to the radiation which is emerged from the surface 2 to outside. So the heat transfer will be the summation of these two heat transfer from the first surface as well as from the second surface. So the heat transfer will be given as So this is the heat transfer from surface 1, and this is the heat transfer from surface 2 or bottom surface. So we need to find the view factor F13 and F23. So let's find the view factors from the charts. So we will be using the view chart to find the view factor here. So there is a chart which usually given in the various books. So I am using the view factor and the ratio of the sides of a given geometry chart to find the view factor. And you can see that in the chart there are various curves or different radius or length of the geometry, different dimension of the geometry is plotted there, and for each curve associated with different dimensions, there is a associated view factor value of that. So usually the chart given for the two parallel plates and the two cylindrical surfaces, cross section of the cylindrical surfaces. So from the chart we can find that. So first we need to define the dimensions here. So my diameter is 75 mm and my length is 150 mm. So which means that so I am writing this in meter. So my R by L value is 0.25. So my R by L value is 0.25 here. That means we have to search for a curve having the R by L value of 0.25, and then we need to look the view factor value from the y-axis. So in the y-axis there are view factor value, and the x-axis there is L by R value, and there are various curves here. So this is my view factor and this is my R by R value, and there are various curves here, and all these curves have different R by L value. So first we need to decide our geometric parameter, which is R by L. So we can fix our x-axis and the particular curve. Let's say this is my curve for my obtained R by L value. Now L by R is just a reciprocal of that. So that means, let's say my L by R is here. So my Fij would be this value which I require. So this is how we use the chart to find the view factor. You can also use the expressions which usually given for different two parallel flat plate or the cross section for the cylindrical surfaces. So if you use those empirical relation, you will get almost the same answer. So but by using these plots, we will get the view factor F23 is 0.056. So we get view factor F23 because we are using these surfaces. So this graph is valid when the radiation is emitted from the bottom surfaces and moved toward the top surfaces. So in our case, the bottom surface is associated with 2 and it is moving toward the top surface here. So this is my view factor F23, which is 0.056. Now we get the view factor F23, and we need to find the view factor F12. That means the radiation emerging from the one surfaces and F13, the radiation emerging from the surface 1 and going towards surface 3. So for this, let's write the summation rule. So the radiation factor F22 will be 0 because the radiation emitted from the surface 2 will not be intercepted by the same surface. So here, for example, this is my surface 2 and the radiation emitted from the surface 2 intercept by itself. That is, the radiation which is coming from the surface 2 fall at surface 2 itself here. So here the radiation view factor will not be 0 and it has some finite quantity. But for the flat surfaces, it is usually a 0 case. Which means I can actually get the view factor of 2, 1. So my view factor of 2, 1 is 0.944. Now we will use the reciprocity theorem. To find the view factor F12. So we already found the view factor F21. So it will be F21 is 0.944 and the area will be given by we need to calculate the value and we will get the view factor F12 is 0.118. So we get the view factor F12. That means the radiation which is coming out from the surface 1 and intercepted by surface 2. Now from the symmetry we can see that the view factor, that the radiation which is coming out of 1 will go to 3 and the same amount of radiation can go to 2 also. So this is because the surface 1 is in middle of surface 2 and 3. So that means half of the radiation will go to 2, will intercept at 2. I should make the straight line because the radiation will travel like this, and half of the radiation will travel at 3. So that means from the symmetry, the view factor of F12 will be equal to the view factor of F13. So by symmetry, F12 equal to F13. So this is actually true for many examples. Like other example where this might be true is, let's say, this triangle, and the each side of triangle is equal, and let's say this is my surfaces. So the radiation will emitted by 1 will reach to 2, and the same radiation emitted by 1 will reach to 3 also. Similarly here, the radiation emitted by 1 will reach at the top surface as well as it will reach to the bottom surface. So here also I can write like this. That means the view factor F12 is equal to F13, which means that the same amount of radiation coming out from the surface 1 will be approached by 2, and the same amount of radiation will approach 3 also, which is coming from the surface 1. So now we get the view factor f1, view factor f1,3. We found the view factor f2,3 by using the charts. So we can just use this relation to find the heat transfer. So I am using this equation 1 to find the heat transfer. So this is my area, and this is my view factor multiplied by Boltzmann constant, and the temperature is. Now similarly, this is my heat transfer from Q to 3. That means from surface 2 to 3. That means from the bottom surface. So from bottom surface, it will be given as my area, my V factor value multiplied by Stephen Boltzmann law for the constant, and just by solving it, we will get the total heat transfer 1830 watt. So I just substituted the value here in this equation 1 to find the heat transfer. So in this question, we first found the view factor. So there are 3 surfaces, and we use the symmetry analysis, we use the chart, and we use the reciprocity rule to find the view factor. So in total, we use the 3 methods to find the view factor. So if you have a parallel surfaces, for example, 2 surfaces which is situated parallel to each other, or either in rectangular shape or in the circular shape, you can use plot curve or the empirical relation which is given in any heat transfer book to find the view factor to these surfaces. Once we find the view factor from these surfaces, we need a view factor from the side surface also. So from using the chart or the correlation, we found the view factor f2,3. Now we require f1,3 also. So for this, we use the reciprocity theorem and the symmetry of the view factor, which allow us to get f1,3. And once we get all the view factor which is required in the heat transfer relation, we just use the conventional heat transfer expression to find the total power rate. So let's move to the different question. There we will look how to find the different view factor in the arbitrary geometry. So in the question 2, we have given the different kind of geometry, and we have given 2 surfaces. And we do not, in the question it is mentioned that we do not need to use the table or chart here. So we need to find the view factor f1,2 and f2,1, and we have given 2 surfaces 1 and 2. And we can see that these 2 surfaces have different shapes, different geometries, and connected to each other with different orientation and all. So let's find the view factor one by one for all the surfaces. So in case of A, this is the geometry. So let's say this is my surface 2 and this is my surface 1. So we need to find the view factor f1,2 and f2,1. So these are the view factors we need to find. So just by clearly looking the figure, we can say that f1,2 will be 1. That means the radiation which is emitted from surface 1, all the radiation actually will reach to surface 2. That means this equivalent to the view factor of 1. So view factor of 1 means that all the radiation emitted from the surface will reach to the other surface. So we can clearly, by inspection, we can see that the the value of F12 will be 1 because all the radiation from the surface 1 is going to reach at surface 2. So by direct inspection, we can see that the value of F12 is 1. Now to find the value of F21, we will use the reciprocity theorem. So here, so this is 1 by inspection. So my F21 will be just the ratio of two different areas. These are my two different areas. So 0.42 will be my view factor F21. That means only 42% of the radiation is emitted by surface 2 and that is reaching the surface 1. Whereas 100% of the radiation which is emitted from surface 1 to surface 2. So let's move to the different geometry. So I will use this dotted line to signify there is no body here, but still there will be some radiation which is crossing this boundary, this dotted boundary. So the inner circle will be the surface 1, the outer surface is surface 2, and the dotted surface is surface 3. So we need to find F12 and F21. So first, again, you can look the figure and you can think that whether you can use symmetry or whether you can directly use the direct inspection, that if the radiation coming out of the any surface totally reaching to the other surface, or if the view factor is 1 in this case, or if the view factor is 0, that means the radiation is not at all reaching the other surface. So in that case, the view factor will be 0. So first you can see the diagram and use this direct inspection method. Then you can use the symmetry that which view factor should be equal to each other. So by the summation rule, so first point we can make here that F11 is 0. That means the radiation which is coming out from the surface 1 is not intersected by surface 1 itself. So the radiation which is coming out from the surface 1 is not falling on the surface 1. It is actually going towards surface 2 and the surface 3. So this F11 will be 0, which means that no radiation is actually falling to surface 1, which is emitted by surface 1. So we can use the summation rule. So this will be 0. And we get, we will get this equation. Now, again, use the direct inspection method or use the symmetry method and see whether you can use the reciprocity rule also. So let's look at the diagram and try to use all these kinds of rules. So by looking at the diagram, I can say that the radiation which is emitted by the surface 1, half of the radiation actually strikes surface 2. and the remaining half of the radiation will strike surface 3. That means we can say that my F12 will be equal to F13 here, because the radiation emitted by surface 1 will reach to surface 2, and the same amount of radiation will reach to surface 3 from the other side. So we will use this symmetry relation in this equation A. And we found that F12 and F13 is 0.5. Now once we found the F12, now we can use the reciprocity theorem to find the F21, because we have F12, and by using reciprocity rule we can find F21. This is my F21 which I want to find. So I already got this. I'm just putting the surface area. So this is my view factor F21. So my F21 is 0.25 and my F12 is 0.5. So here you can see that we use symmetry rule, summation rule, as well as the reciprocity rule to find the view factors. So let's look some other geometries as well. So the bottom surface is my surface 1, and the top cut surface is my surface 2. So again we can just directly looking at the geometry, and we can found that the amount of radiation which is emitted by surface 1, the all radiation will reach to second surface. There will be no loss of radiation or no intercepting radiation by surface 1 itself. So here F12 equals 1. Now once we get the F12, we need to find F21, and we know that we can just use the reciprocity rule. So this is 1, so which is basically A1 by A2. This is my value of F21. Now suppose we need to find F22 also. We need to find the radiation factor F22. So as I discussed in question 1, that for the flat surface curve, let's say this is my surface 1. Oh, okay, let's say this is my surface 2. For the flat surface, this F22 will be 0. That means the radiation coming out from the surface 2 will not reaching surface 2 itself. It is just going out from the surface 2. But if it is a curved surface like this, then this can happen. That means the radiation which is coming out from the surface 2 can reach surface 2 itself. And similarly like this. So here F22 will not be equal to 0. So in this case also F22 will not be equal to 0, because the radiation which come out from here can reach the surface 2 itself. So the radiation which is coming out from the surface 2, it will be intercepted by itself, like this. So we can use the summation rule for this. So we already know f21. So we can find f22. 1 minus 0.63. So this is why, sorry, f22. So let's move to the problem D here. So in the problem D, I have this flat surface which is connected to the inclined flat surface. Let's say this is my surface 1 and this is my surface 2. Now I am again using dotted line to show there is some imaginary surface which I will be representing by surface 3. So again by inspection we can say that f11 is 0, f22 is 0, f33 is 0. So these are our basic observations just by looking at the diagram. By summation rule from at surface 1, so this is my summation rule. Again my f11 is 0, so I have only this expression. And again the amount by inspection itself, we can see that the view factor, that means the radiation emerged from surface 1 will reach to surface 2, and the half of the radiation will reach to surface 3 as well. So we have assumed that this side L3 and this side L2 is same. So in that case, the half of the radiation will reach 3 and the half of the radiation will reach 2. So there is a symmetry in the view factor. F12 will be equal to F13. So we use this relation in equation A. We can find F12 and F13 are 0.5. So now if we want to find F21, we will use Reciprocity Theorem. We know this and we need to find this. So my F12 is 0.5. So this will be my view factor for this arrangement of the surface. So let's look at the last shape, E. In the last part of the problem, we have given a flat surface and there is a ball which capped at the surface. Let this flat surface is surface 2, this surface is surface 1. Now the radiation from 2 will go above also. So let's create the imaginary surface here, which is surface 3, which means the radiation from 2 will definitely cross surface 3 also. So again you can use the direct inspection method, symmetry analysis, summation rule, as well as the reciprocity rule. All these 4 rules to determine all the view factor here. So just by looking at the diagram, you can say that F22 is equals 0, F33 equals 0, because the radiation coming from surface 2 will not be intercepted by itself. And same goes for the surface 3. So again, we can see that the radiation which is emitted by surface 1 will reach surface 2, and the same amount of radiation will reach surface 3 also. Now we have, so I already actually discussing this since half an hour. There can be the exception from this rule. For example, let's say this is my arrangement. This is my surface 2, 1 and 3, and this length is say L1, and this is length is, let's say, L2, and L1 is, let's say, smaller than L2. So in this case, I cannot say that the radiation emitted by surface 1, and there will be some radiation emitted by surface 1 to 3. So there will be radiation emitted by surface 1 to surface 2, and will be the radiation which is emitted by surface 1 to surface 3. And in this case, the F1 will not be equal to F13. So this is purely a geometric concept here, because the length L1 is not equal to length L2. That means the unequal amount of radiation. Here the unequal amount of radiation will reach surface 2 and 3 from surface 1. But since here you can see that this distance from the center of the circle to the surface 2 and surface 3 is equal, we can use the symmetry analysis to say that these view factors are equal, because the radiation coming out from the surface 1 will reach to surface 2 as well as surface 3 equally by equal amount. So we can use the summation rule again. And we find this 0. So we put this symmetry rule in the summation rule to find that F12 and F13 is 0.5. And now we know how to find F21, because we got F12, we just can use the reciprocity rule. So this will be my view factor of F21. Now this surface 2 has infinite dimension. That means my A2 will be infinite, because my surfaces don't have a bounded dimension. It has infinite dimension, which is we are actually dividing 0.5 with some infinite quantity. That means my F21 will be 0 here. If my area, surface area A2, or if the length of this surface has some finite dimension, in that case F21 will have some finite number. But in a question it is given that it has infinite dimension. So basically you are dividing some quantity with infinity. So which makes that view factor F21 equals 0. So in the second question, we actually discuss a different geometry, different orientation of the surfaces, and we found the view factors by using 4 rules: summation rule, symmetry rule, reciprocity rule, and we also use the direct inspection method. Just by looking at the geometry, you can figure out where there is a total of 100% exchange of the radiation. In that case, the view factor will be 1. And there may be some surfaces where there is no radiation heat exchange will take place, and their view factor will be 0. So let's move to the third question. So in this question, there is a circular ice ring 25 mm in diameter is enclosed by a hemispherical dome. And if the ice dome surfaces have maybe approximated as black body and are at 0 and 15 degrees Celsius respectively, what is the rate of radiative heat transfer? In the question, it is given that there is a ice surface and it is surrounded by a dome, hemispherical dome. So this ice surface is surface 1 and this dome is surface 2. Then we need to find the heat transfer from this dome to ice sheet 1. So we need to find Q21. That means the radiation coming out from the dome to ice sheet, which is surface 1. So my expression of the heat transfer will be so we need to find the view factor F21. So we already solved a lot of many questions, many view factor of many geometrical cases, geometric surfaces cases in the last question. And so it is pretty clear by much now that how to use different rules to find the view factor. So just by direct inspection, you can find that the F11 will be 0. The F12 will be 1 because the radiation emitted from surface 1 will, all the radiation will be intercepted by surface 2. So that means there will be 100% radiation heat exchange from surface 1 to surface 2. And if we know the F12, we can find F21 by using Reciprocity Rule. So we use all this rule several times by till now. So F12 is 1 here. So but by just plugging the value of area A1 and A2, so since we need to find this quantity, I can just need to evaluate this quantity only. So my F12 will be A1. So A1 is given as pi by 4, 25 square, 291 meter square. So my F21A2 is 495 meter square. So I can directly use this relation here in this heat transfer relation. So just putting the value 495 multiplied by Stephen Boltzmann constant. So here we need to write the temperature in the Kelvin. So my heat transfer will be 3.69 10 to the power 4 watt. So this is pretty simple question. We just use the symmetry analysis here to find the view factor as well as Then we find the heat transfer. Similarly, if you want to find the heat transfer from radiation 1 to, from surface 1 to surface 2, it will be given as A1, F12. So this will be the relation in that case. So let's move to the different question. So in this question, consider the arrangement of the three black surfaces shown. Area A1 is small compared to A2 or A3. Determine the value of F13. Calculate the net radiation heat transfer from A1 to A3. And we have given the dimension area of A1 0.05 meter square, and the temperature T1 1000 Kelvin and T3 is 500 Kelvin. So we have given the geometry here. So let's say this is my surface A1, this is surface A2, this is surface A3, and the remaining surface, this surface is A4. So these are the areas of the respective surfaces. So first we need to find the view factor F13. So which is obviously required to find the heat transfer from surface 1 to 3. So my heat transfer will be given by this relation. So we anyway need to find this view factor F13. Since there are multiple surfaces, it is better to write summation rule first from surface 1. Now, just by looking at the diagram or the geometry, by inspection we can get many of the view factors. So, for example, my F11 will be 0. That means the radiation emitted by surface 1 will not be intercepted by itself. So there will be no falling of radiation into surface 1 coming from the surface 1 itself. So my F11 is 0. In the similar manner, my F14 is also 0 because the radiation will not be falling on. It can't be fall on surface 4. It will travel straight line to surface 2 or surface 3. But this cannot happen. So my F11 and my F14 is 0. That means these two can be vanished. So for F12, since in the first question I told that if you have parallel surfaces arranged parallelly in the vertical direction, either it is a rectangular sheet or the spherical surfaces, you can either use the plot to find the view factor from I to J, or you can use some correlation to find the view factor. So the correlation and the chart you can find in any of the textbook. So in the question 1 we use the chart. Now in this question we will use the correlation. So my F12, so this is my surface 1 and this is my surface 2. So my F12 will be given in such case as d square by d square plus 4l square. So d is the diameter and l is the length of the cylinder. So just by calculating, I get F12.36. So I got F12. Now I can find F13 from this summation rule. my F13 will be 0.64. So now I can use equation A to find the heat transfer. So I just need to put the values here of area, V factor, and we already know the Boltzmann constant and we know the temperature. So just by putting the value here, we will get the heat transfer as 1700 watt. So again, this is quite straightforward problem. So we are given the multiple surfaces. So we use the summation rule first, and then by direct inspection method, we found out the view factor of easy surfaces like F11 and F14, which is 0. And then we use the geometry that there are two parallel surfaces. So in that case, we can either use chart or some empirical correlation to find the view factor, and you can easily find these things in the books. I mean, the chart and the relation of the view factor in such geometry. So we get F12 view factor from this. And then we use the summation rule itself to find F13. And after finding F13, we can find the heat, radiation heat transfer, Q13. So let's move to the true and false question quickly. So we need to identify which statement is true or false. So the first statement says that a body at a thermodynamic temperature above 0 emits radiation in all directions over a wide range of wavelength. The amount of radiation emitted from surface at a given wavelength depends on the material of the body and the condition of its surface as well as the surface temperature. Therefore, different bodies may emit different amounts of radiation per unit surface area even when they are at the same temperature. So this is actually a true. So in the radiation emitted from the surface is depend upon the geometry of the surface, the nature of the surface, as well as if the radiation is diffusive, the radiation emitted out is diffusive in nature or it is moving in a specific direction. Here. So based on all these ideas, even if the surface has temperature equal, so let's say my temperature here T1 and T2 are equal, based on the properties or the nature of the surface, it will have a different, it can emit the different kinds of radiation. It also depends upon the emissivity factor. So if the surface has more emissivity, that means it can emit more radiation. It can also depend on the reflective property rho. That means if some radiation is coming and it hit the surface, how much amount of radiation it will reflect back. And it depends upon the value of reflectivity factor. So all these different parameters, different factors says that even if you have a temperature T1 and T2 equals, that means these both surfaces are at equal temperature, the radiation might be emitted from these two surfaces can be different. So the first statement is true. The second statement says that the black body is defined as a perfect emitter and absorber of radiation at a specific temperature and wavelength. No surface can emit more energy than the black body. A black body absorbs all incident radiation regardless of wavelength and direction. Black body emits radiation energy uniformly in all directions per unit area, normal to the direction of emission. The black body is a diffuse emitter. So again, this statement is true. That means suppose I have a black body. So if the amount of radiation it can receive is actually highest compared to the normal body which is not a black body. So here the tendency of absorb the radiation is quite less in this case compared to the black body. So the black body can absorb highest amount of radiation when we compare to the conventional bodies. Now once black body absorbs all the radiation from the surrounding, it can emit all the radiation outside. So the black body is not only a perfect absorber of all the radiation, it is also a perfect emitter. So it can emit all the radiation, but for the conventional body, the degree of emissivity of the radiation, the degree of how much radiation is actually coming out from the surface is actually depend upon the emissivity factor. But for the black body, this emissivity factor is 1. The tendency of absorbing the radiation, that is absorptivity factor, is also 1. So the black body is actually perfect absorber and perfect emitter of the light or any radiation. So the statement 2 is also correct. That means the correct statement is A, true. So again, let's move to different true and false question here. So it says that for a black body, the radiosity is different from the emissive power since a black body reflects all radiation incident on it. So let's first analyze the statement here. So it says let's define the two bodies. This is my black surface, or I should write black body surface, and this is my some random conventional surface which is not a black body. So the radiosity is actually defined by the total amount of radiation which is coming out from the surface. So that means the radiation can come out as if when the surface is actually emitting the radiation. So this is a surface which is emitting the radiation, and the amount of surface that it can emit, it actually depends upon the emissivity factor epsilon. Now the radiation can also go out after reflecting some part of the irradiation. So let's say this is my R. So there is a radiation which is actually hit the surface, and after hitting it reflects back some amount of radiation. So this is my radiosity actually. So it contains the radiation which is emitting from the surface and also the reflected part of the radiation which is coming out from the surface. So, but in the black body, we already discussed in the last question that it is a perfect emitter and perfect absorber. That means in a black body, there is no reflection can happen. So it can emit all the radiation. So my emissivity is 1, and my tendency of reflectivity, the reflectivity factor is 0, and my tendency of absorbing radiation is also 1. So in the question it is given that the radiosity is different from the emissive power, so which is actually the incorrect statement, because all the radiosity here in the black surface is due to the emission of the radiation, unlike the conventional surfaces, which is where the radiosity is due to the emission of the radiation as well as some reflecting part from the incident radiation. So there is an incident radiation which got reflected, and this reflected part with the emissive radiation part make the radiosity in the conventional surface. Since the reflectivity is 0 in the black surface, the radiosity will be only due to the emission of the radiation. So my first statement is not correct. So my option is B, false. Similarly, the second statement says that the spectral intensity for emitted radiation can be defined as the rate at which the radiation energy is emitted at a wavelength in a direction per unit area normal to the direction. So that spectral intensity is actually depend upon the specific direction. That means my radiation is actually coming out at some angle theta from the surface. So this the intensity due to this radiation is called the spectral intensity. Similarly, if my radiation is coming out in all directions, so this is my diffusive intensity. So that's all for today. So we actually had one question number 5. So that question I will discuss in the next week. So for this week, we have discussed question related to the view factors as well as the heat transfer, the different geometry which contain the concept of the view factor. So we see that the arrangement of different shapes and oriented at different direction can affect the view factor and the radiation heat transfer also. So next week we will solve some more question to the related to this radiation heat transfer. So thank you.